few months ago I made a video on rocket nozzles that you can see in the background here, and since then I've wanted to return to the subject in a little more depth, as rocketry is a subject I'm very interested in, and I feel the short controlled detonations I was doing in this previous stuff wasn't really doing the subject justice, as they're just a short spike of power rather than a continuous flow. This, of course, if used in anything in reality, is more akin to a gun firing than a rocket propelling itself upwards, because you want the force to be over a longer period of time where it can be easily controlled. This, however, isn't possible using my previous methods for two reasons. Firstly, the plastic bottles and the 3D printed nozzles can't withstand a sustained heating from any combustion going on within them. And secondly, I've no way to add any more propellant as it's used up, because I simply had the hydrogen and oxygen that was in the container, and once that was gone, that was gone. So over lockdown I've decided to build myself a hybrid rocket engine out of much stronger materials, so I can properly go into the subject and make something that I could investigate nozzles and fuel types and other such in much more detail. So just in case people don't know, I'll briefly describe how a hybrid rocket engine works. In essence, you have a oxidizer tank, a fuel, and then a nozzle to expel the gas. Usually the oxidizer is the fluid and the fuel is the solid. This is because solid oxidizers are quite unstable and quite rare. So general convention is that the fluid will be the oxidizer and the solid will be a fuel. That's what sets hybrid engines apart from liquid engines, where both of them are fluids, usually liquids, but you can have liquid gas ones in some cases. Or of course in solid ones where they're both solids and they're just mixed together very finely. So it's fairly simple. The oxidizer is simply put under pressure via either a compressing gas or a turbopump, and then it is fed through the fuel, and where the oxidizer and the fuel meet you have combustion, which of course produces high temperature gases, as in most things, and then it operates the same as any other rocket engine, with the compressed high temperature gases going into the nozzle and expelled out the nozzle after being accelerated by it. I have explained how this works in my previous video on nozzles, but I will preface what I said before, that only happens if the flow at the throat is choked and therefore exactly sonic for the specific gas you have at that specific temperature and pressure. If not, it instead functions due to the Venturi effect, which actually means that your nozzle will slow down the outcoming gas. So it's very important that at the choke point the flow is going at the speed of sound in whatever that is. For my oxidizer, I'm going to use nitrous oxide simply because it's the easiest thing to get hold of. It can be bought online. There's small 8-gram canisters sold for use in sort of whipped cream kits. They're very easy to get your hands on. So I've designed this. This is where the canister is going to interface with the rest of the rocket, and the general idea is that it fits in the top here, and then there are two holes, one down the middle that will contain a screw that will be able to pierce the canister, and then the gas is able to go into this tube here, or it'll be controlled by a valve through here, and then it will exit through a pipe soldered onto the gap here. And then the other important part is of course the nozzle, which is here. This is a fairly simple design. You have the bell nozzle there. You have an area that can be tapped, so it can be screwed onto a combustion chamber. My taps can't tap all the way onto the end, so this space here is simply so that the threads run the full length of this part here, rather than just sort of petering out around there at the limit of what my taps can cut. And to make it easy to screw and unscrew, I've got a nice hexagonal bolt here. That's just going to make it a lot more easy to take the thing off and on. If I go again to show the way through, again it just constricts the flow. You've got a thin choke and then it opens it up again. I'm not too bothered about this central part coming in the cast, because this is 1.5mm and that is the smallest diameter of drill bit I have, so if it doesn't cast properly I can just drill the hole out. But this itself won't cast too well, because you'll have problems with air bubbles. It's really small, that's only 7mm in diameter for reference. So this is going to have sprues added to it to allow the air to escape whilst it's being cast. So I have created this design. Basic idea is you've got an easy place to pour in from the top there. It'll go down and the air is able to escape up these 3 sprues, and then any metal that ends up in there can just be cut off at the end and filed down. So in essence, I'm going to get this printed off on my 3D printer, and I'm going to go through the standard thing you've seen me do a couple of times before. The only difference is it's 3D printed rather than wax. So I'll print it off, I'll I will pour the plaster of Paris around it. I will then let the plaster of Paris set over a couple of days, and I'll cut back when I have everything at the forge ready to do some casting. In a change from what I've done previously in my metalworking, I'm not actually going to treat the moulds and melt everything out in the oven. This is partly because inside those is 3D printed plastic, which of course I don't want getting inside the oven, it could ruin everything, and partly also because occasionally when I've done it before it's just created massive amounts of smoke and set off all the smoke alarms in the house. So instead I'm just going to put them above the forge for a little bit and leave them in the fire till everything melts out, and then I'll go and I'll put my crucible in. So currently my crucible is just sitting to the side there. There's a little pile of brass that I'm going to use to cast next to it, cut into pieces. That's actually an old fire guard that I found lying around, but it's going to be put to much better use as a prototype rocket engine. So that wasn't intended. Hopefully none of the moulds are damaged, but yeah, it seems got a little hot. Even for this, that was hotter than I expected. So brass is to temperature, and just to make sure that everything goes well, I'm now going to repurpose the blower I have for the forge to create some negative pressure down one of the air outlets. Haven't tried this before, no idea if it will work, but it's a rudimentary form of vacuum assisted casting if it works, and should help me get the very best. So here's the brass out with its wonderful popping sounds. Now I'm going to pour the brass into the mould. As it's cooling, and of course that will solidify over a certain amount of time. I can take this out, pick up the mould and drop it into some water. Now I'll do that with all of the other moulds, and then I'll cut back when I'm seeing what I've got. And here we have our 5 cast blanks ready to come out. So start with the biggest. So this is the bit where the nitrous oxide container is going to attach to, and I'll just break away the mould. It's always the tense part, but it is looking good so far. It's looking very nice so far, actually. Very, very nice. Oh. If all of the casts are like this, then I will be a very, very happy person. Right, on to the next one. Oh. Slight defect there, but that's all looking very good. Next one. Some mould wasn't the best, so there might be some extra metal I need to take off this one. But again, it's not bad. It's got a lot of excess metal, so this might not be the best one. But yeah, the when I was pouring for the mould for this one, I noticed that some of the plastic powder set a little too early, so it's not conformed perfectly. That's good. Next. Ooh. Oh, that's weird. Extra bit off there. Seems like we've had a void. Bit strange, one or two extra bits. But not bad, still got the nice hexagonal part. Those can just be cut off afterwards. And finally, once again, it's come out really well this time for the casting. I am really happy with this, if you couldn't tell from my voice. So again, nice hexagonal, nice bell. Getting some of the stuff out from the inside will be a bit of a faff, but I have no trouble with that. Okay, so the next job's going to be to get the last bits of all the plaster out, properly drill holes, and then start tapping everything to work. But yeah, this is really good. I now have one of my nozzles with all the sprues cut off and then filed down, and as you can see, it's rather nice and it's starting to look how it should. But it's not quite a nice flat sheen surface on the outside, and for tapping the end I do want that to be a set 7mm diameter, so I need to machine it down, but I don't possess a lathe. I do however have an alternative, but anyone who's an actual machinist probably wants to look away now, because what I have is a drill in a vise. Now what I can do is I can put part in the drill, tighten it up, and in a move of machining heresy, take a file, turn the drill on, and very carefully put the file against the surface of the metal and start machining it down just by putting the file along the surface. I really hope that none of my workshop technicians find this video. After my improvised machining, I now have this, and as you can see, it's got a very nice, smooth, clean edge on it. And this, if I get my calipers, is almost exactly 7mm in diameter. So this will tap quite nicely. So the next job is to put the taps onto the end and then to drill a hole through to form the throat. thing that's needed, of course, for a hybrid rocket engine to go with the oxidizer is a fuel. And for this I'm going to use paraffin wax, partly because candles are really easy to come by, and it actually works quite well as a fuel because it vaporizes very quickly. And of course, the faster you can get the fuel into a vapor form from its solid, the faster it can burn. So mostly in hybrid rocket engines they are of this type. They've got a solid fuel and a gaseous or liquid oxidizer. And for mine I just want a sort of core that I can insert into my combustion chamber to make it reusable. Because this is a sort of project that's designed so that it can be used multiple. I do not have the resources to make a new combustion chamber for every time I want to run the things, because of course with large solid rocket boosters they are manufactured and single-use components. So I'm going to make this as I've just got a tube the same diameter. I'm going to pour the wax in and fill it up. But you also need a hole down the middle to allow the nitrous to flow. So I've now got a tube that's just about the right outer diameter I need, and I'm going to slowly put that down the middle whilst everything's still nice and liquid, and just hold it there for a second whilst everything solidifies. And then just of course leave it until the wax starts to set, or until you get impatient, in my case. Because I can just take it out of the vise carefully. Take the stick that's keeping it in the bottom and just get some water, and that'll cool it a lot quicker. So now the next thing that needs to be done is getting, of course, this core out. Now I'm going to do that. So I'm going to clamp this in the vise pretty tight. Going to get a nice piece of wood with the right diameter. I was using for blocking the bottom before. And I'm just going to knock it out. Pay attention to the fact I'm keeping the tube in for the moment, just so that the force here doesn't collapse the hole down the middle. And you have to be a little gentle with this and a little careful, because of course you do not want to break any of the parts that you're working on at the moment, and wax is just a little fragile, so it should come out at the end. Just knock it a little further. There you go. Break off the solid end. And now you've got a nice wax tube. Just cut off the end. Make it look nice and neat. And neat ends aren't just aesthetic, of course, it means it's going to fit in to the rocket better. So now I've got a nice wax cylinder that can be used as the fuel for the rocket. Here we have the completed engine. So I'll talk through generally. So we have our combustion chamber here, which screws onto an inlet, which has a straight pipe through to the canister holder. This screw acts as a valve. It has a hole drilled through it in the direction of the cut marking there. So in this configuration it is open, and if turned 90 degrees it will then be closed. The canister can then slot into the back here, at which point a screw on the rear tightens it slightly, and if tightened any further we'll begin to press that into a spike that is located inside the canister that can be adjusted by this screw here. I can show you that. It slots out this 3D printed casing just by turning it 90 degrees. So then if I get light, so there's clearly a spike there, and then just a little mark hole in the lower part that you can just about see there that leads on through to this pipe. After the pipe, you of course have the combustion chamber. Both of these have been sealed using Teflon tape, and inside here is the wax tube that forms the fuel. Now finally here I have an electric igniter. This is an Etsy's electric igniter, just fairly cheap off the internet, but I have painted the section all up to around there on the ends. This means that the wires won't short circuit, because of course it has to run through the metal igniter and through a very small hole. So of course make the legs close together, separate them a little bit, and push them through. Until you have the igniter at the other end of that, at which point the whole assembly can be inserted into the end of the rocket and tightened until a good seal is achieved. At which point, of course, separate the legs. You can see it moves back and forth. Get it in as best I can, and then I'll fold these two sections down into either side so that they can easily be attached to an igniter. To properly load the canister, got a little silicone ring, just cut a hole in the middle of the piece, put that over the end. Just make sure that it seals properly and doesn't leak. Goes in there, and of course angled, put in, put out this screw so it locates a bit better. And of course when I'm ready to launch, I get a screwdriver, I tighten that whilst making sure that valve is closed, at which point the valve is opened slightly, then a current is sent to the wires, and then the valve can be opened the full way. Test of the hybrid rocket engine, number 1. So I have the canister in place, and I'll tighten the screw. Canister is punctured, seal is held in position. Second high-speed camera is recording. Ear defenders are in place. Insert safety key. Red light is going. Turn on a small amount of flow through the system. Okay, I'm not hearing anything. Maybe the rubber gasket's blocking it off a little. Close the valve a little more. Quite completely closed there. Okay, audible confirmation of gas flow confirmed. Ready to ignite engine. In 3, 2, 1. Engine ignition seems to be confirmed. Opening valve. Now ready for test number 2. So the first test, there seemed to be real trouble with the actual piercing of the cartridge, so I've sharpened the spike to do that. And there also seemed to be a lack of a pressure build-up to actually get the engine started. So I've added a wax plug to the end of the nozzle that will be blown out if the starting is successful, and I've added just a little bit of match heads into the end of the combustion chamber, hopefully just to give it a little more of a kick to get it started. So I'm going to tighten here, listening very carefully, see what I can hear. Yes, I'm sure I heard it pierce then. I'll start my other camera going for high speed. And open the main valve after loosening this a little, just to make sure the spike's out the way, because the other problem we have is flow rate. So we've got a little bit of noise now, it's definitely coming out. Open the main valve, so it's free now to travel into the chamber. Key is inserted, light is on, circuit complete. Launching in 5, 4, 3, 2, 1. I see smoke, it's definitely lit. See if anything happens. I'm listening this a little bit. So for the third test, I've made a few more minor alterations. I have put some methanol on the inside of this, just so you've got something that's in vapor form to begin with that can start the reaction. I've improved my wax plug to make it a lot more secure, and I've put a larger wrapping of tape around here to make a better seal to there, because I don't know whether my gasket inside is doing enough job, because you seem to have to retract it a fair distance so that it comes back off the spike to get flow. So I am going to close the main valve, set my camera recording, find my glasses. Just remember, safety first. Now tighten. Launching 5, 4, 3, 2, 1. Plug failed to eject. So for the fourth test, I have ditched the wax plug again, because actually the first one was one of the best runs, and I don't know whether limiting flow and also having real trouble hearing, as you saw last time, when the thing has actually been pierced. So I'm going to try it without the plug. Again, I've still got the edge thing started, still got some methanol in it, and I'm just going to tighten up the screw. Right, we have airflow going through. Just a little more. And 3, 2, 1. That definitely sounded and smelled a lot more like a proper start. Alright, we have airflow going through. Loosen it a little more. And 3, 2, 1. Now, as a post-mortem of that last test, I've taken everything apart and I've found that the igniter, the sparks that were seen, must have been burning iron, because the two ends of the igniter, these were found just in the end here, sort of around in there, had burned down to the point of the throat, at which point they'd stopped burning, clearly through lack of temperature, I think, because of contact with the brass. The inside of here looks pretty much entirely burned out, and if I put my piece of wood through and push out whatever's left... Oh, okay, so the wax is still quite warm, but there's clearly still a fair amount of wax there. So it didn't burn through all of its fuel, but that is nowhere near as long as the initial part was, so it has burned through a fair amount of it. So that's useful to know. On closer inspection of the canister is actually still quite cold. There wasn't actually a very good piercing here. It was more like the one from the first test, which is this, and you really can't see any gap. The difference with this is that, of course, it was still leaking after I'd finished, so I took a hammer and knocked it in. A reason for the lack of piercing, I think another split is formed in my 3D printing. So this part here, this was what failed the first time I tried. I didn't have the... actually, I may have the video for that. So effectively, this part has been the weak part in both cases, because you actually need quite a lot of force through this screw to actually get it to pierce. So I think the next upgrade I'm going to need to make to this is to really improve the piercing part. So I'll unscrew that and show you effectively what that looks like, but that's going to be the main focus of any upgrades I do to the system, because it's just not reliable. It's really difficult to pierce the cartridges, and it's not doing it reliably, and it's being in the way. So preferably I could do with making a way that pierces it and then has channels in the side. So if I say I cut some channels going down through this, so that once it's pierced the container, the air has somewhere to bypass this part, and this isn't in itself forming a blockage that's keeping the canister closed. For this as well, you may have seen I'm having to hold it like that when I'm sort of compressing the cylinder to get it pierced. That's because it likes to wobble around, so some better guide rails to hold it would probably be very useful. Not sure how I'd implement that. Possibly, if I had a tube it could go into, and then push down a full tube where it's contacting on like 4 guide rails, and and then have something in the top that comes in locks and then the screw can come from. But that's going to have to be redesigned. The nozzle performed perfectly well. The igniter performed perfectly well. The fuel appears to perform well. Little bit of trouble with the gasket, but this was only very, very simple. All in all, I'd call this a very successful test. It was more fourth time lucky than third time lucky, but yeah, I'm really happy with how this turned out, and I'm going to continue working on it. So I hope you've all enjoyed, and I will see you once I have completed the improvements to this design.